Hi, I'm Kaya Kleno, a participant in the 2018 Data Intensive Scientific Computing REU at the University of Notre Dame. In my project, I studied the application and optimization of deep learning techniques for particle physics data. This is a view from inside CERN's data center, where hundreds of petabytes of data from the Large Hadron Collider are stored and processed. The Large Hadron Collider is a particle collider at CERN that accelerates proton beams to almost light speed and records their interactions when they collide. But there are around 600 million collisions every second, which would correspond to about a petabyte of data per second, and only about 1 in a million are scientifically interesting. After an initial screening, data from about 1,000 events per second is sent for reconstruction, a process which must accurately distinguish the handful of interesting collisions from the remaining background data. The signature produced by this collision, for example, is consistent with the Higgs boson decay but also with an insignificant background process, demonstrating the difficulty and ambiguity in reconstruction. One possible solution to this dilemma lies in neural networks, algorithms modeled after how the neurons in our brains learn by communicating with each other in a complex network. A deep neural network approximates a function or process by mapping inputs to their target outputs, with hidden layers of nodes acting as variables. There are connections between each node, but it learns a given function by adjusting the weights of each connection as training data is passed through it. When seeking to optimize neural networks for processing momentum vectors, we noticed that for simple single-variate functions, the error consistently decreases as the number of nodes increases. However, for multivariate functions, such as coordinate conversion, this added complexity leads to a lot more fluctuation and unpredictability in performance. After finding the optimal network for conversion, we decided to integrate it in a multi-step process with vector addition, combining it with the intuition we gained by optimizing simpler networks. We tested structured networks where each individual step was optimized versus black box networks for the same task, and surprisingly, the black box networks performed better in all trials. This implies that we still have more understanding to gain about how to optimize networks for simple, multivariate functions and multi-step functions. Regardless, deep learning remains a powerful tool with promising applications in high-energy physics.